In 1968, deep inside General Motors engineering buildings, a quiet decision was made. Not about a big block monster, not about a fire-breathing 427, but about an engine that most people today barely even remember, the 307 cubic inch small block. Now here's the strange part. This wasn't supposed to be a performance engine. It wasn't meant to dominate drag strips. It wasn't built to headline muscle car brochures. On paper, it was just a filler engine, a corporate compromise, something designed to sit between the tiny 283 and the more aggressive 327. The boardroom discussions were simple. GM needed an engine that could power mid-level sedans without cutting into the profit margins of their flagship performance mills. They needed something efficient enough to satisfy fleet buyers, but powerful enough that nobody would complain about acceleration on highway on-ramps. What they created was supposed to disappear into suburban driveways and rental car lots. But what almost nobody knows is this so-called economy V8 quietly became one of Chevy's most underrated Trans Am era weapons. You think you know the story of late 60s racing? Not like this. Because in the late 1960s, America was obsessed with cubic inches. Bigger was always better. Magazine covers screamed about displacement figures like they were holy scripture. Car guys measured each other's worth by how many cubes sat beneath their hoods. Ford had the 428 Cobra jet. Chrysler had the 426 Hemi. Plymouth was stuffing 440s into anything with four wheels and a prayer. And Chevrolet was busy cramming 396 and 427s into everything that moved. Dealerships couldn't keep big block cars on the lot. Insurance companies were losing their minds trying to calculate risk premiums. And teenage kids were working double shifts at grocery stores just to afford the monthly payments on something with enough power to light up the tires. It was chaos. Beautiful, horsepower-fueled chaos. But racing didn't work like that. The SCCA's Trans American Sedan Championship had rules, strict ones. These weren't arbitrary guidelines designed to annoy engineers. They were carefully crafted restrictions meant to keep competition close and prevent manufacturers from simply buying victories with unlimited budgets. The centerpiece of those regulations was simple but devastating for anyone who worshipped displacement. Engines had to stay under 5.0 liters. That meant no 396X, no 427s, no big block glory. All those corporate bragging rights about cubic inches suddenly meant nothing. The monsters that dominated straight-line acceleration were completely useless when officials pulled out measuring tapes and displacement calculators. Suddenly, brute force wasn't the answer anymore. Now the war was about efficiency, balance, revving power, and survival. Because Trans Am racing wasn't a quarter-mile sprint, it was sustained brutality. Multiple hours of high RPM operation, constant cornering loads, brake zones that demanded engines survive dramatic deceleration, followed by immediate full-throttle acceleration. Any weakness in design would reveal itself not after thousands of street miles, but after dozens of punishing laps. And that's where things got interesting. The Chevrolet 307 small block debuted in 1968 with a bore of 3.875 inches and a stroke of 3.25 inches. That gave it a total displacement of 307 cubic inches, or just about 5.03 liters, right on the razor's edge of Trans Am legality. Engineers had essentially backed into the perfect displacement almost by accident while trying to create an economy engine for commuters. It used the same crankshaft as the 327, but paired it with the smaller 283's cylinder bores. The block itself shared the same basic architecture as its small block siblings, meaning parts interchangeability was excellent. Compression ratios varied depending on configuration, but the standard L14 version ran around 9.0.1 and produced roughly 200 horsepower with a 2-barrel carburetor. The camshaft was mild. The intake manifold was nothing special. The exhaust manifolds were restrictive cast iron logs designed for quiet operation rather than maximum flow. Nothing impressive, right? Exactly what GM intended. But there was a problem. Not with the 307 itself. The problem was with what came before it. Racing teams had been trying to make the 327 work in endurance applications, and the results were creating nightmares for engine builders across the country. At high RPM, the 327's longer stroke had a weakness: oil starvation. Once you pushed past 6,000 RPM, the oiling system struggled to keep up. The crankshaft was spinning so fast that centrifugal forces were flinging oil away from bearing surfaces faster than the pump could replace it. Bearings overheated. Rod journals began to score. The thin film of oil that separated metal from metal would break down under combined thermal and mechanical stress. Mechanics would later say that after long high-speed runs, the bearings looked like charcoal briquettes. Dark, brittle, completely destroyed. Some engines came back from testing with bearing material embedded in the crankshaft journals so deeply that no amount of polishing could save them. The cranks went straight into scrap bins. And in endurance-style road racing, that was a death sentence. You can't win a 3-hour race if your engine grenades itself after 90 minutes. The 307's shorter 3.25-inch stroke changed everything. Piston speeds dropped significantly at high RPM. This might sound like simple math, but the implications were profound. At 6,500 RPM, the average piston speed in a 327 could exceed 3,500 feet per minute. Those pistons were traveling nearly 40 miles per hour while slamming back and forth thousands of times every 60 seconds. In the 307, piston speed stayed closer to 3,200 feet per minute at the same RPM. That difference reduced frictional heat. It minimized rod stretch. It decreased the inertial loads trying to rip connecting rods away from crankshaft journals. And most importantly, it helped the oil film survive. When you reduce the violence happening inside combustion chambers, everything lasts longer. Bearings stay cooler. Rings maintain better contact with cylinder walls. Piston skirts don't develop the kind of micro cracks that propagate into catastrophic failures. But that wasn't enough. Because the 307 had inherited the same basic oiling system architecture as every other small block Chevy, and that architecture was designed for street driving, not sustained high G cornering at triple-digit speeds. During early testing, engineers found metal shavings in the oil pan after extended track sessions. The shavings were aluminum and copper, bearing material that had been scraped away during momentary oil film failures. Oil pressure would fall off dramatically during sustained high G cornering, sometimes dropping from a healthy 60 psi to barely 20 psi mid-corner. On long right-hand turns, oil sloshed away from the pickup tube toward the left side of the pan. The crankshaft would briefly run dry. For fractions of a second, metal touched metal with nothing in between, and over hundreds of laps, those fractions of seconds accumulated into destruction. And then, the real nightmare started. Connecting rod bearings began to seize at sustained RPM above 6,800. The failure mode was consistent and terrifying. First, oil pressure would fluctuate wildly as the compromised bearing created additional clearance. Then temperatures would spike as metal-to-metal contact generated friction heat. Finally, the bearing material would actually melt and weld itself to the rotating journal. One test engine reportedly lasted less than 40 laps before the crankshaft welded itself to a main bearing. The engine didn't just stop running, it locked solid. The rear wheels of the test car skidded as the drivetrain suddenly became a single frozen mass of metal. The driver nearly lost control at over 90 miles per hour. When they tore the engine apart, the main bearing had essentially become one piece with the crankshaft. No amount of force could separate them. The entire rotating assembly was scrap. So what do you do when your safe engine starts self-destroying? You rethink the oiling system. Chevy engineers went back to fundamentals. They studied oil flow patterns using dye testing and pressure mapping. They discovered that the stock oiling system was prioritizing oil delivery to components that rarely failed while starving the components that always died first. So they modified the internal oil passages. prioritizing oil delivery to the main bearings first, then the camshaft. Instead of feeding the top end before the crank, the revised layout pushed pressurized oil directly into the rotating assembly, the part that always failed first. The theory was simple. Valve train components could survive brief oil pressure drops. They weren't under the same loads as crankshaft bearings. But the rotating assembly needed constant, uninterrupted oil flow, or it would destroy itself within minutes. Simple, brutal, effective. They also experimented with oil pan designs. Baffles were added to prevent oil from sloshing away from the pickup during cornering. Windage trays helped strip oil from the rotating crankshaft counterweights, returning it to the sump faster. Some competition versions used dry sump systems that eliminated the oil starvation problem entirely by storing oil in external reservoirs. With improved oil flow and lighter rotating assemblies, the 307 could now survive sustained operation at 7,000 RPM. Race-prepped variants pushed compression to 11.0.1 using forged pistons machined from aircraft-grade aluminum alloys. Larger 2.02-inch intake valves replaced the stock 1.94-inch units, improving airflow at high RPM. Connecting rods were shot-peened to improve fatigue resistance. Main caps were machined and fitted with ARP studs instead of factory bolts. Every component that could fail was either replaced or reinforced. Horsepower jumped from the stock 200 to well over 350 in competition trim, but more importantly, torque stayed usable. Around 340 lb-ft at mid-range RPM meant drivers could exit corners without waiting for the engine to come alive. They could apply throttle earlier, carry more speed through apexes, and accelerate harder while competitors with peakier engines were still waiting for their power to arrive. Compared to the peaky 302 used in factory Z28s, the modified 307 delivered smoother, more predictable throttle response. Drivers reported that the power felt connected in a way that some higher-strung engines didn't. You could modulate throttle position precisely and expect proportional responses from the drivetrain. At tracks like Laguna Seca and Riverside, that mattered. Laguna Seca's famous corkscrew demanded immediate throttle response as drivers plunged downhill through elevation changes. Riverside's long, sweeping corners rewarded engines that could maintain power through extended high RPM operation. Both tracks punished engines that either hesitated on throttle application or overheated during sustained full throttle runs. In testing during the 1969 Trans Am season, development mules running 307-based engines reportedly shaved nearly half a second off lap times compared to earlier small block builds. That doesn't sound like much until you realize that races were often decided by margins measured in tenths of seconds. Quarter-mile testing showed times in the mid-13-second range at around 104 mph in lightweight chassis. These were trap speeds that rivaled some factory muscle cars running engines with 50 more cubic inches. The 307 was punching well above its displacement class. Not bad for an engine nobody took seriously. But racing is never that simple. By 1970, the world was changing. Emissions regulations were creeping in from California and spreading eastward like an incoming tide. Compression ratios dropped across the board as manufacturers scrambled to meet new standards. Lead was being phased out of gasoline, and engines designed for 100-octane fuel suddenly had to survive on 91. Insurance companies started charging outrageous premiums for anything labeled high performance. A 19-year-old buying a muscle car might face monthly insurance payments that exceeded the car payment itself. Sales of performance variants plummeted as practical economics crushed youthful enthusiasm. Suddenly, building screaming 7,000 RPM race engines didn't make business sense. The corporate accountants took over. Performance divisions saw their budgets slashed. Racing programs were scaled back or eliminated entirely. Engineers who had spent years developing competition engines were reassigned to emissions compliance projects. Production versions of the 307 continued using hydraulic lifters and mild cam profiles. Horsepower ratings fell like stones dropped from a bridge, first to 180, then to 170 by 1971 as compression dipped below 8.5.1 to accommodate low lead fuels. The same engine that had been turning 7,000 RPM on racetracks was now struggling to motivate 2-ton sedans with any enthusiasm. And just like that, the magic faded. Street cars like the Camaro, Nova, and Chevelles still carried the 307 on their option sheets, but now it was seen as an economy option. A grocery getter engine, something your dad's Malibu had, not something you'd expect to see tearing through apexes at 120 miles. The enthusiast magazines stopped writing about it. Performance parts catalogs didn't bother listing 307 specific components. Speed shops pushed customers toward 350 swaps instead of 307 builds. Within just a few years, the collective memory of what this engine had accomplished simply evaporated. Most people forgot what it was capable of. By 1973, the Clean Air Act had effectively killed high-compression small blocks. Catalytic converters were on the horizon. Emission testing was becoming mandatory in major metropolitan areas. The entire philosophy of engine design shifted from maximum performance to minimum pollution. The 307 limped on until 1974 before Chevrolet finally ended production. Tooling was repurposed for other engines. Performance variants vanished from parts catalogs. Engineering drawings were archived in filing cabinets where they would gather dust for decades. No farewell tour, no celebration, no retrospective articles honoring its accomplishments. Just silence. The engine that had quietly proven itself capable of sustained high RPM competition simply faded into obscurity. Junkyards filled with Novas and Malibus carrying 307s that nobody wanted. Engines were scrapped for their core value rather than rebuilt for their performance potential. But here's the twist. Decades later, engine builders began rediscovering the platform. It started slowly. A few curious mechanics noticed that 307s seemed to tolerate high RPM better than comparable 350s. Word spread through forums and garage conversations. People started experimenting. The 3.875-inch bore allowed for safe overbores of up to 0.040 inches without compromising cylinder wall thickness. Combined with modern aluminum cylinder heads featuring improved port geometry, rebuilt 307s started showing impressive dyno numbers. With aftermarket cylinder heads and modern roller cams, rebuilt 307s were producing over 400 horsepower reliably. And because of the shorter stroke, they revved like crazy. Lightweight rotating assemblies meant lower reciprocating mass, reduced stress on the crank, higher safe RPM ceilings compared to traditional 350 builds using longer 3.48-inch strokes. Builders who had been fighting rod stretch and bearing failures in over-revved 350s discovered that 307s would spin past redline without complaint. The engineering advantages that GM had accidentally created 50 years earlier were still relevant in a world of computer-controlled fuel injection and digital ignition mapping. It wasn't just nostalgia, it was engineering. Today, collectors chase big block Chevelles and LT1 Camaros. Auction houses celebrate the usual suspects: LS6 cars, ZL1 engines, Copo specials with documentation folders thicker than phone books. Magazine features focus on the same dozen legendary power plants while ignoring everything that fell outside the spotlight. But hidden beneath decades of misunderstanding, the 307 remains one of the smartest small block designs of its era. It didn't rely on brute force. It relied on balance, durability, and the simple idea that sometimes less stroke means more survival. Because the truth is, the 307 didn't become a Trans Am era powerhouse by accident. It survived brutal testing, overcame oil starvation failures, and quietly delivered the kind of high RPM stability that bigger engines couldn't match. Engineers who worked on the project went on to design later performance engines carrying lessons learned from the 307 program. The emphasis on oiling system reliability, the attention to bearing loads, the respect for piston speed limitations, these principles didn't disappear when the 307 left production. They just stopped being associated with the engine that taught them. It may not have had the headlines, but it had the endurance. And in racing, that's what wins. If you enjoyed this story, let me know in the comments what forgotten engine you want to see next. And make sure to subscribe so you don't miss the next deep dive into the machines that changed performance history forever.